My name is Callie Wilson, and this is my Physics 2211, Lab 5, the Slinky Test. Introduction. The purpose of this lab is to observe the motion of a vertical slinky and how the physical nature of the slinky affects its descent due to gravity. The first model will be made with GlowScript. The other model will be made with the Tracker app. The results show similar outcomes in both models, that the slinky remains stationary after the initial drop and accelerates at a constant rate afterwards. The initial conditions are the mass as 0.25 kilograms, the position 0, negative 9.2 times 10 to the negative fourth, 0 meters, and then the velocity is 0 meters per second. The system is the Slinky, and the surroundings is the Earth, and you can see a free body diagram down in the corner. Some equations that will be needed, F-grav and F-drag, and then of course the velocity update formula and the position update formula per usual, and the law of conservation of energy. This is a screenshot of the tracker and the graph that it had made. As you can see, the Slinky was tracked as it went down. It's not very clear from the image there, but that's what happened. Now, as for the glow script, here is a screenshot of my code. You can see the while loop starting from 1.7.17 because that's when the graph on the previous slide, if you could tell, started the descent and the actual movement on the graph, the slope, and then you can see the equations used, the velocity update, the position update, to calculate what I'm looking for with the spring. And then here is what it comes out with once you play the code. The results. First off, I would like to take into account some errors before we really get into the results. One of which being that the mass of the Slinky was just an estimate, so the end velocity of the results could have been a bit different. The height of the Slinky as well in the video was just estimated, so a difference in that would have affected the bottom of the Slinky. Additionally, drag could have affected the Slinky as well because it was not actually accounted for. And obviously, human error is always present. So the GlowScript model is always not going to have these things and account for these things. And unlike real life, so it's always going to be a bit different. Now, time for the actual results. In the bottom left, you can see a position time graph, and that is from the GlowScript graph because before on the tracker slide, you saw the tracker graph. And as you can see, the slope, similar timing, the 1.71. And then we have a direct comparison on the graph in the top right, which the blue line is the tracker and the red line is the glow script. And you can directly compare the two glow script graphs, see that it actually is that same results, and you can see that roughly around 1.71 the action gets started with energy in the Slinky going down. Now, what does this mean? Because the Slinky is not a rigid object, internal and external forces apply on the bottom of the Slinky. The Slinky, once released, accelerates at a rate of 9.81 meters per second. But not every part of the Slinky does. The center of mass of the Slinky accelerates at that rate, but the force of tension within the Slinky and the force of gravity are equal at every point below the center of mass as it initially falls. Now, what if a weight was attached to the bottom of the Slinky? I suspect that there would be similar results with only a change in velocity between having a weight attached or not. All in all, that's the results of my lab and the end. Thank you.